Hello everybody, my name is Jeff Koss and I am doing this presentation for a class that I'm studying at the University of Advancing Technology. The class is CSC-382 and it is a computer science programming class that deals with data structures and algorithms. For this assignment, I had to make a binary search tree. And it was difficult at first because I didn't have much experience with it. But in the end, I think I did a pretty good job. So let's get into the code here. I use hold on a second here. I am in the wrong one. Here we go. Okay, that's better. I was going to say that was some old code there. So, okay. So here's what I'm looking at right here. So I had to make a binary search tree. And in doing so, I had to do something kind of unique. Um, I usually have a separate file for classes, right? Right. When you're programming object-oriented programming, the rule of thumb is that each class should be in its own separate file. At least that's what I was taught. But we're using templates with this one, and that threw me for a loop. I've never used templates before. So I was having an issue with it. Well, with templates, that C++ file that you were using uh, can no longer work the way it's supposed to. So you have to basically make it into a header file and then include that into your source file. And yeah, so that was cool. So I learned something new there. Okay, but let's just get into the code. So I take a pretty straightforward approach with this. We're just going to go through the source code, first here, and then I'll get into the other header files and stuff like that. So I basically have a class. It's called binary search tree, and we basically instantiate an instance of that. We do it a little differently though. Because we're using templates, you have to declare what type it's going to be. So we use integer here. Okay, and I'll get more into that in a little bit. So the name of the object is called search tree, and it is equal to binary search tree as an integer. That's how it works. So I basically throw in 9 different numbers, 9 different nodes, in various just randomization, and then that's what all of this is for. So all of this code is basically what it's doing is it's calling the root and it's saying you're going to insert it's going to equal to the insert node of, of this. Insert node is a function inside of the binary search tree class. So let's get into that. So we do that, and I have another function called preorder, and this is going to go from left to right. Okay, and then we have an in order, and it's going to go left root to right. And then we have post order, which is left, right, root. So it'll print all of these numbers out in different sequences, basically, depending on how you order it, which was a requirement. Another requirement was to figure out the maximum value of the binary search tree, and I have a function that does that. It's right here. And then it goes into I start deleting some things because of the fact that this assignment wanted us to delete things in various areas. So I did that. I deleted from the root number 25, number 30, and number 60. So if you look at the tree, you will see that one of these deletes is for just basically a single delete with no nodes attached to it. There's another one with one node attached to it, and another one with 2 attached to it. And we have, and in order to do those things, the code is a little different. And I'll show you how that works. But what I did is I made it all encompassing. So I'll show you that. So here's the header file. Um, we do use templates with this one. Templates are new to me. I struggled with this for a moment. Templates are very useful if you're writing generic code. I can see this being useful for um, some IT stuff where you're going to be generating code and then implementing it over different systems to do different things. So you might use this for a data set of integers or a data set of strings, whatever. Well, now you have the power to go ahead and do that on the fly, which is really, really neat and it's powerful. I just have to get used to thinking like that, which is something that I haven't before. So, but once I got it implemented, it works good and I can see the use for it. Moving on, I make a class called Node. How do I explain this? It's basically, I'm going to be honest with you. I don't like using class here because it's misleading. Um, Even though this is considered an object, it's really a structure. And I'm sorry, but I'll have to disagree with, I guess, my teacher on this one. And I'm sorry to say this, but I think that there should be a structure, and for the reason that you're just storing data in it. You're not really, this isn't really going to be an object until later on. So I didn't really understand it at the time. I understand it now. Now that I wrote the program and see a different perspective of how it was implemented. But just getting into this, I probably would use a structure from now on. So that's just apples and oranges. That's just my opinion on it. You know, um, we do a class called binary search tree. This is basically the only true class that's in it. And here's the thing. So you see this here where it says node root. Well, basically, that's what this class is for. This is where you create your nodes. See, and that's where it gets tripped up because I personally use structures for this because um, what are you saying? You have a class inside of a class? It doesn't really make a lot of sense to me in that aspect. Um, so even though I respect my teacher very much so, and I would never um, go above him or anything like that. I think that me and him could debate this all day long, to be honest with you. But that's what makes it so neat. That's what makes programming so neat because there's so many different ways to do this. Anyway, moving on. I have a constructor here. It's just a basic constructor binary search tree. And all it does is inside of it, it's going to set root equal to 0. And basically, that's just a placeholder, right? So when you start a binary search tree, you got to start somewhere. Well, 0 would be the greatest place in the world to start. So that's what we do. And then we make use of these nodes classes. Um, I have an insert node, a delete node, a minimum value node, which I'll get into later. And then we have a couple of functions. We have a pre-order function, an in-order function, a post-order function, and a max value function, which is not a node function. So, and then we have a private function called getNode. And basically, this is a placeholder. So that's my header file. Now here's what's tripping me out. So this would be the C++ file that accompanies the header file. But because we're using templates, it doesn't work like that. And my professor had to actually drill this in my head in order for me to understand it. And it makes sense now. Because we're using a generic form, it really can't be a C++ file because it wouldn't understand it. So we do it this way. So I have, again, this is just basically the guts of all of the functions that we get into. I'll get into them briefly because I want to keep this short. Um, Binary search tree, delete node. Okay, this was the one I had to work on the most because it was very tricky to do this. When you delete a node from a binary search tree, um, I'm going to be honest with you, it's a lot like surgery. It's very precise. A surgeon has to be very precise with his hands and that scalpel when you're doing surgery. And it's the same thing here for removing something from a binary search tree. when you're dealing with a node, because you can get into a lot of trouble. It could start pointing to basically stuff that it shouldn't be. So you have to be careful. So I have this. Okay, the base case is going to be if root equals null, then you're just going to return the root. So that means if there's no root, you're just going to return it. There's no list. But anyway, if the key to be deleted is smaller than the root key, then it lies on the left subtree. So then we delete the node to the left of the root. If the key is to be deleted to greater than the root's key, then it's on the right subtree. So we do the same thing, but to the right. Now, that makes sense because of the way a binary search tree is structured. Obviously, certain numbers go to the left and certain numbers go to the right. We all know this. So if the key is the same as the root key, then this is the node to be deleted. So there's no child there, so you're just going to delete it. It's going to return null. If it only has one child or no child, this is how you're going to handle it. You're going to go to the left. Left is going to equal to null. Okay. And then we have a node called temp, and that's going to equal the root, and it's going to shift it to the right, and then we're going to free that root, and then we're going to return temp. Else, we're going to go to the left and do it to the left. So if it has two children, this is how we handle it. We get the minimum value of the node to the right, right? Then we take the root's key, which is the data basically in it, and we equal that to temp to the key. And then we delete the in order successor. So what we do is we take the root to the right, delete the node to the right, and give the key a temporary value. And then we basically shove the new value into there, and that's how it works. Okay, given a non-empty binary search tree, return a node with minimum key value found in that tree. All right, so this was kind of tricky. So this is the minimum value of the node, and we have another node called current. Node. While current and current to the left is null, we basically shift current to the left. Okay, so that's simple. Like I said, these things are simple. Maximum value, well, it's going to go to the right, obviously, because it's going to be a greater value. All right, so getting the node, we basically make a new node, and it's going to be a generic. And then we assign it a key, which is the value, and then node left, node right, it's going to be null. And then we return the new node. And then basically, when we insert the node, we have a function for that. And then we use the root. If the root is null, then we return get node and the value in that node. Now, if the root key is less than the value, then the root key is going to the right, and we're going to insert that node to the right with the value. If the root key is greater than the value, then we're going to shift it to the left and insert the node on the left hand side. So does that make sense? That is exactly how a binary search tree works. So I'm rambling on here, but it is the way it goes. So pre-order, okay, so this function basically does a pre-order. There it is, right here. Okay. In order traversal, here you go. Here's your in order traversal right here. Left. Post order traversal. It's all right there, and that's pretty much the end of it. So let's check this out in action. Source. And we're going to fire it up. All right. So it inserts the nodes as I wanted them to. These are just random positions. There's no order to it. Okay. So this is the first traversal. Obviously, it goes from lowest to highest. Okay. Now this one, this is your second traversal. Okay. This is basically an order. The max value on the binary search tree is 100. That is true because we don't have a value that's greater than 100. So that works. We delete 25. We do an in order traversal of the modified tree. So obviously, if you look at an in order traversal, which is the second one here, you can tell 25 was deleted, and it just goes in sequence to the highest number. delete 30 now, and that works. So 30 is gone, and everything is shifted the way it's supposed to be. And we delete 60, which was in the middle here. So basically, we have to cover two different nodes, and that works out perfectly. Okay. And there is the end of the program. So everything is met. Everything is good. I'm ready to submit it. Anyway, thank you for your time. I really do appreciate it. Bye-bye.